All right, welcome back. This is Mr. Fawcett, and we are about to start the second part of our lesson involving finding the limits of trig functions. We're going to go down to page 3, if you have those notes out, to number 5. In our last lesson, we talked about some relationships, formulas, identities involving trig functions that we could use to simplify a limit expression, right? So in the past, we've factored and we've rationalized, but in our last lesson, we learned some new techniques specifically for when we had limits that involve trig. So today we're going to learn some more, things that can help us simplify those more complicated limit expressions. So I'm just going to start reading off what I have up here. Sometimes there are trig functions that cannot be manipulated algebraically, so we must determine their limits using tables or graphs. Now, the first helpful limit that we're going to look at, and again, we're going to see this limit pop up in future problems, and if we know what this limit is equal to, it will help us simplify problems down the road. And maybe you'll see what I mean once we get to an actual practice problem. But for now, we just want to figure out what this limit is equal to. And there's no algebraic manipulation we can do here to figure out what it's equal to. There is a proof for this. It involves a concept we may look at a few lessons down the road called the squeeze theorem, but it's beyond the scope of what we're doing right now. So we're going to use a table to approximate this limit like we did in the first couple of lessons. I already filled in the table for you. We are approaching 0. We are looking at the whole limit, so we're approaching from both sides. And you can see as we approach 0 from the negative side, we seem to be approaching 1, and as we approach from the positive side, we also seem to be approaching 1. So both of our one-sided limits are 1, and if both of our one-sided limits equal the same real number, then that means our actual limit is also going to be equal to that. So this is a key relationship we're going to take forward. The limit as theta approaches 0 of sine of theta over theta is equal to 1. Now, again, that's a tool we're going to put in our toolbox, and we're going to break it out when we see some practice problems later on in this lesson. We have a couple more limits to work through, though, before we take a look at those problems. On the next page, we are going to look at a similar function. So, again, this is going to be our goal, to figure out what this limit is. The only difference is that instead of just having theta inside of our sine function, we have 3 theta, and we also have the same constant in our denominator. So, and we'll get to generalizing this rule in a second, but let's just take a look from the table. As we approach 0 from the negative side, we are approaching 1, and as we approach 0 from the positive side, we are approaching 1. So both of our one-sided limits are 1, which means our actual limit is equal to 1. Okay, and now we want to generalize this, because that constant may not always be 3. It may be 2. It may be 10.6. So based on what we just observed, what inference do you think we can make about the value of the limit as theta approaches 0 of sine of c theta over c theta, where c is any constant? So essentially, what if we had something like this? Would this limit also be equal to 1? The answer is yes. We can generalize this rule. Again, we're not working through a proof here. We are just using some data to make an informed decision, and you are going to have to take my word for it that this does work in all of these cases for whatever constant c is. Okay, so hopefully we have this written down and we will be using it later. Our last one, before we start some practice problems, deals with a limit involving cosine. Okay, so this function or limit involves a cosine instead of a sine, And again, I filled in the chart. As we approach, so we're looking at the limit of 1 minus cosine of theta all over theta as theta approaches 0. So as I approach 0 from the left-hand side, we are approaching 0. Okay, these numbers are getting less and less negative. On this side, the numbers are decreasing, and we are also approaching 0. So both of our one-sided limits are 0, which means our actual limit is 0. The three limits that we boxed in purple, I would encourage you to keep those handy as we move forward, because again, those are tools in our toolbox for us to be able to simplify more complicated limits down the road. Let's clear this and let's get to some practice problems. All right, and we will hopefully get through 2 practice problems and we'll be done with this video in hopefully, around 15 to 17 minutes. I know some of the other ones have gone a little bit over that 20-minute mark, so I'm trying to keep them shorter. Let's look at number 2. Again, in your head or out loud, say what you should do when you first see a limit expression before we do any type of fancy manipulation. Okay, hopefully you said direct substitution, because that is always going to be our first step. I'm going to try direct substitution with our numerator. And this gives us sine of 0, which is equal to 0. With our denominator, it's a little bit more clear that it's going to be 0. Which means we have an indeterminate form. Okay, so because we see some trig in our limit expression, we're probably going to need to use some sort of trig manipulation. We may also need to factor, but we're likely not going to need to rationalize any numerators or denominators because we don't see any radicals. I'm going to let you think about which of those 3 limits we just boxed above, so the 3 new ones that we just learned, which of those 3 could we apply to this limit expression to help simplify it? Okay, while you're doing that, I'm going to clear this work. You can, of course, pause the video because I assume you'll need more time than 10 seconds to look through them. But once you're back, you've probably saw that this limit expression looks like a couple of the ones above, but it doesn't look exactly like any. So the 2 that it looks like, first would be the limit as theta approaches 0 of sine of theta over theta is equal to 1. And the other one would be the limit as theta approaches 0 of sine of c theta, remember c can be any constant, is also equal to 1. Now, again, this limit expression right here, this function, there's a constant in the sine function, but there's no constant in the denominator. So it kind of looks like it's somewhere in between these 2 limits. It's kind of a part of both. But we need to make it look like one or the other, right? We know that they're both equal to 1. So as long as we can make it equal to one of them, we know that we can simplify and just say that portion of the limit expression is equal to 1. Now you may want to pause the video and see if you can use some algebraic manipulation to either get a 4 as a factor in the denominator, so that there's a 4 in the sine function and in the denominator, or maybe there's a way to get rid of the 4 inside of the sine function, right? So that we have no 4s in either the numerator or the denominator. So it's up to you. Pause the video, do some work, and see if you're able to make it look like one of the purple ones. Okay, so after you've been working, one of these will be a lot easier, and that's going to be to make the denominator also have a factor of 4. And the way that I'm going to do that is I'm just going to multiply both the numerator and the denominator by a factor of 4. So I'm going to get 4 sine of 4 theta over 4 times theta. Now you may say, Mr. Fawcett, well now there's an extra 4 in the numerator. Well, there is, but using our limit properties, I am easily able to move that outside the limit, right? So now I get 4 times the limit as theta approaches 0 of sine of 4 theta over 4 theta. And we know, based on what we looked at up above, that this limit right here has to be equal to 1. So I have 4 times 1 is equal to 4, and that is the answer to this limit expression. Okay, let's move on and do number 3, and then I think we're going to call it a video. Yep, number 3 has a little tangent going on, so that'll be good to look at. Okay, first thing we're going to do is substitution. So the limit as theta approaches 0 of tangent of theta is equal to tan of theta, or sorry, tan of 0. And you may have to think back of what tan of 0 actually is. It may help to rewrite in terms of sine and cosine. So this is one of the relationships we wrote down above. Tangent of theta is equal to sine of theta or sine of 0 rather. Let's get this correct. Over cosine of 0, which gives us 0 over 1, which gives us 0. So the limit of our numerator is equal to 0. Limit of our denominator, fortunately, is far less work. That's also going to be equal to 0. So we do get an indeterminate form, which means we're going to have to plug away at some sort of trig manipulation. All right, let's erase this, give ourselves some more space. And I kind of gave you a hint, right? I kind of said, can we break tangent down into something that's sine of theta or cosine of theta? Because the 3 limits that we boxed above, the 3 that we learned today, none of them have tangent in them, but they all either have sine or cosine in them. So maybe if we can rewrite tangent in terms of sine and cosine, we may be able to simplify it using one of our limits that we learned earlier in the video. So I'm going to break this down. The limit as theta approaches 0. Instead of tangent of theta, I'm going to have sine of theta divided by cosine of theta. This is all over theta. Okay, now the key thing here is simplifying this complex fraction. So I think an easy way to write these out is to have sine of theta over cosine of theta times 1 over theta. So if you're not sure why these are equivalent, take a second, go through the algebra of separating the fractions and then multiplying them together. The easy way is, remember, dividing by a number is the same thing as multiplying by the reciprocal, right? Which is what we did down here. So this still may not be clear as to what we need to do. Remember, we are trying to get this limit to look like one of the 3 above. I think we can safely roll out the 1 minus cosine of theta all over theta because there's no subtraction going on here, which means we are left with 2 limits to look at. We're left with the limit as theta approaches 0 of sine of theta over theta, or the limit where we just throw a constant inside of our sine function and a constant in our denominator, right? And I can just actually leave this up here because the constant could always be 1, which is when it would look like sine of theta over theta. So is there a way for us to manipulate what I have in red to get sine of theta over theta? And there is. It just means we're going to rearrange our fractions again. So I'm going to get the limit as theta approaches 0 of sine of theta over theta times 1 over cosine of theta. Okay, so again, I'm just rearranging my fractions without changing any values. And now I can use a limit property, right? So this is going to be equal to the limit as theta approaches 0 of sine of theta over theta times the limit as theta approaches 0 of 1 over cosine of theta. Now, we can simplify this limit, right? We know that's equal to 1, and then we can evaluate the limit involving the cosine. So we have 1, I'm going to use direct substitution on the other, times 1 over cosine of 0, which is equal to 1 times 1 over 1, which is equal to 1. Okay, again, I encourage you to go back and work through the algebra on your own if you're not really sure about how we went from one step to another. But again, using those 3 special limits up above, they can make some of these more complicated limit expressions solvable and easier for us to evaluate. So I'd encourage you to work through numbers 1 and 4. You also have, I believe there's some extra problems on the next page as well. Yep, 4 more. So there's quite a bit of these trig limits to work through. Take your time. You may have to try multiple methods, multiple manipulation techniques, but eventually you can get there. Okay, this is Mr. Fawcett. Enjoy the rest of your day.